Well, this says something about the cardinality of a union of, let's say, I'll say it in terms of A1, A2, A3 out to maybe N, if these are finite sets. Okay? Then the number of things in the union okay, well, my Venn diagram, if I tried, is not going to look very accurate, but we can think. First of all, we add up all of the individual ones. So this is all overall I. I goes from 1 to n. Maybe I will write this, although I won't be writing it on all of them. We have n of them. Oh, I know what I'll do. It'll make it match the other ones. This is overall I. And then there are, well, there's n choose 1, which is n terms here. And this is will match when we start doing some other ones. Then we subtract off the sum, I'll just say I not equal to j of these intersections. And here there are n choose 2 terms. Okay. And then we will add back the sum. Well, again, we cannot have I equal to j, also not equal to k. We need them all to be distinct indices of triples. Here we have n choose 3 terms, and this will continue. This is what I was saying. When you include, you exclude, you include, you exclude. The minus signs, they shift, they alternate, I should say. First, you add up all the individual things. Then you subtract off all the intersections. You add back all the triples. Guess what? Subtract off all the 4 tuples, like this, the intersections of them, okay? At the very end, so the next one would be a minus. Oops. And then we have a dot, dot, dot. The very end, well, we come to the intersection of all n terms. A1 intersect A2, intersect all the way out to A sub n. And we have to figure out the appropriate power of minus 1. Here we have 1 term is positive. We have 2 terms is negative. 3 terms is positive. This suggests the power is a minus 1 to the n plus 1, or n minus 1 is fine too, like this. So you have all the singles, subtract off all the intersections of pairs, add back the intersections of triples, subtract off the intersections of 4 tuples, like this. Include, exclude, until you get to the very end. And it comes with a minus 1 to the n plus 1 power. Okay, this is inclusion-exclusion, and I'm about to use it on 2 functions. This is going to be fun, I will say that, but it's going to get intricate. Okay, we'll be okay. So suppose the cardinality of A is n. Cardinality of B is M. And now, because I want to count them, I'm going to give it a name. Let's say T is the set of all F from A to B, such that F is onto. Now, we will assume that N is bigger than or equal to M, because we know, and we have proved, with pigeonhole principle, that if n is less than m, the answer is, or this cardinality T is the empty set. So I'm really interested in when it's not empty, let's count the number of things in T. Well, part of the reason I started with m is 3 is because it was a little bit less intense than the general case, and hopefully this will go through a little easier having seen m is 3 already. So I will define C1 to Cm, these are all inside U, where U is all functions from A to B, and let's say Ci is all functions from A to B such that Bi is not in the image of F. And again, I forgot to do it this time, but let's do it now. I'll put it in parentheses again, that B, we will just say it's B1, B2, out to Bm. So we have M sets, C1 through Cm, and each one says that, or the ith set says that Bi not in the image. Okay, so just like when we had M was 3, we have similarly that this T, maybe I'll say notice T, as I've defined it, which is all onto functions, it's this all functions but set difference C1 union C2 union Cm. For the exact same reason as before, if you are not onto, it means the image of F is not all of B, and that would say that one of these BIs, at least one, is not in the image, so you would be in one of these, right? So if you take all functions minus this, what we are left with is precisely the onto functions. And so we can count the cardinality, or the cardinality of T is the cardinality of U. Okay, also, I'll mention this now, the cardinality of U, we know. We can still think of it as a list of length n, f of a1, f of a2, f of a3, like this, where the elements this time, instead of coming from a 3-element set, they come from an m-element set. So this is m to the n. Okay. So now is when we get ready for inclusion-exclusion. I would say strap in, hold on to something. Here we go. Cardinality of T equals, well, is going to be m to the n minus the cardinality of this union so this is m to the n. Here is where I'm going to start using inclusion-exclusion. We have minus, okay? We have the sum of cardinalities of the individual ones. And as I mentioned, there are m of these, m choose one of these, right? There's m in total. Okay, then I subtract the sum over all Ci intersect Cj. Again, I is not equal to j. And I mentioned there were m choose 2 of these. Then I add the sum of all Ci intersect Cj intersect Ck, where I, j, k, they're all different indices. There are m choose 3 of these. We would then subtract off the intersection of all 4s, add back the intersection of all 5s, etc. But I will just go to the end. It's going to be a minus 1 to the m plus 1, and then we have the intersection of all of them. Intersection C, the last one is a m, like this, parentheses. Well, now comes the counting. But you see, based on what we thought about already, it's really not bad. I would say this looks more overwhelming than it is because there's a lot of indices and a lot of sums. Okay, so here we go. Let's start counting. m to the n minus big parentheses. Okay, we're going to go one by one and think about these. First of all, this is the just single sets, just the number of things in each one. And first of all, for each of these, how many terms are in the sum? And then we count. Okay, how many terms are in the sum? There are choose one, terms in the sum. And then maybe I will think about some stuff below, which I might erase. This will be my little side work. So any of these, the cardinality of Ci, okay, this is very much like we already thought about, where you have this string or list of length n, f of a2, f of a1, right? But in this set, you can put, this can be anything in B except bi. So you have m minus 1 possibilities for f of a1. You have m minus 1 possibilities for f of a2. This continues m minus 1 possibilities here. Okay, before, when this was only 3, remember, we had, well, there were two, like this. But general m, you have m minus 1 to the n. Okay, so this is this quantity because every single one of these terms is the same number, m minus 1 to the n, and there are m choose 1 many terms. Okay, this argument will be similar for each, well, until we get to the end. Now, then there's a minus. Now again, and I mentioned this when we first wrote the general inclusion-exclusion, how many things are in this sum? Well, there are m choose 2. M choose 2 in the sum. And then, down here I will think. This is my thinking. I'll leave it up until I need to erase it. If I count this, Ci intersect Cj, of course, I is not equal to j. F of a1, f of a2, etc. to f of a(n). Well, b1, or excuse me, bi and bj are both not in the image. And so I have m minus 2 left in here. M minus 2, m minus 2, out 2, m minus 2. This cardinality you can see, right? And it's the same anytime I is not equal to j, because it's the same number. You just can't map to bi and you can't map to bj. So you have m minus 2 elements of b you can't map to. It's this. So each one of these has cardinality m minus 2 to the n. It's going to be a plus. How many terms are here? Well, if these are all distinct, and that's what I mean when I write that I, j, and k are all distinct indices, we have m choose 3. And then, if you think down here, how many are in any one of these? Okay. Well, the only thing that changes, if you want to look at the cardinality of Ci intersect Cj intersect Ck, where I, j, and k are different indices, is you have, now there's 3 things from B that you can't map to. So you have m minus 3 choices. M minus 3 all the way out to m minus 3. The pattern is exactly what we've seen, and this pattern will continue exactly like this, except this is when we really have to think some, okay? Let's think about the very last term here, this one. And then we will finish the sum. We'll put up dot, dot, dots and put whatever comes at the end. You see this one, just like when we had only 3 sets. This one says B1, B2, well, all the way out to BM. So every single element of B is not in the image. Well, if you're mapping from A to B and no elements of B are in the image, there's no functions like this. So this cardinality here is 0. Just like we saw when B was 3, the intersection of all 3, C1, C2, C3 was 0. But we can't just leave this as a dot, 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 because it would look like it goes forever, and it certainly does not. So that means that the last non-zero term, well, what's it going to look like? It will look something like this. I'll just write out one of them because I don't have to do so many I's and J's. We will have, instead of an m plus 1, it's going to be a minus 1 to the m. It's the term right before, okay? Then we will have this many terms, okay? In the last non-zero term, well, the cardinalities look like this. They look like this. C1 intersects C2, intersects C3, out to, there's an intersect, Cm minus 1. It's not only this one, it's all possible intersections where only one of the sets is not there. Okay, so for instance, you have C2 to Cm, C1 to Cm minus 1, and you have a total of m in total, which is this quantity here. Let's just count this one because they all have the same cardinality as we have seen in the other terms. What does this say? This is all functions from A to B, such that B1, B2, B3, B4, all the way out to Bm minus 1, not in the image. There's only one thing here, and it's you have this Bmth thing, and you have all these other ones not in the image. It maps every single element of A to this, okay? I got to put one more so that, well, okay, I could keep adding. I just needed to make it to where we have more things in A than we do in B. All right, that's what we're counting here. But you map everything to Bm. That's the only possible function here. So this cardinality is 1, and similarly, any of the ones where you have m minus 1 of the different sets intersected, they just all map to whichever element is not included as a set here, right? If that makes sense. So it maps to Bi if Ci is not in this. So all of these have cardinality 1. This is the last one. Now, then there's a parentheses, which I will also close in blue because I opened it in blue on this side. Well, this is the number of onto functions. It's quite complicated, especially compared to like one-to-one functions. But we can make this formula slightly, ever so slightly simpler. So I can continue here. And there's a pattern, right? M choose 1, M choose 2, M choose 3, etc. This one does continue the pattern. If I put an M choose 0 in front of here, nothing has changed because M choose 0 is 1 and the coefficient in front of here was 1 to begin with. Then, of course, I have to distribute the minus sign. So this would be negative, this would be positive. Like this, I would be distributing the minus sign across. So this is equal to a big sum. And look at the bottom index. This is going to be my summation notation. So K will go from 0 to m minus 1. And then, okay, wonderful. What do you notice? Well, we have a minus 1 to some power, which we will do at the end because I also have to think about distributing. Then we have m choose k. We have m minus k to the n. And now I'm ready for my power. When k is 0, it should be positive. When k is 1, it should be negative. Don't forget to distribute. When k is 2, it should be positive. When k is 3, it should be negative. Well, okay, this is just a minus 1 to the k, like this. So, all of this work, inclusion and exclusion, which was a lot of fun. We all get to hear. This is the number of onto functions.